CIT 1121, Module 11, IPv4 addressing. We're going to go through a whole bunch of IPv4 stuff here. A lot of the basic stuff is in this particular chapter. I found it. What I found is this: we're going to have some supplemental instruction on this, but I might as well go through the slides given to you by Cisco Academy, just so we make sure that we hit the points that they're looking for here, and then we're going to get deeper in on some future videos that you're going to watch later this week. All right. So IPv4 module addressing, if we go to the next slide, it's just going to give us a rundown and say this is the things that we're going to take a look at here. First, we're going to look at the structure. Then we're going to look at the type of messaging that we can send out, unicast, broadcast, and multicast. The different types of IPv4 addresses, like public versus private, and APIPA addresses, and multicast addresses, so we'll look at those there. Network segmentation, how a broadcast domain works, which we've talked about before, so that should go by pretty fast. And then we'll get into subnetting itself and look at how we can subnet networks of different sizes and how we can tailor the sizes of the networks that we want to create based on the number of hosts and number of devices. And we can create a subnet range that'll make a network that'll be about that size that will be able to support whatever it is you want. You can use as fewer number of addresses as possible. Because I don't know if you heard about this, but there's only 4 billion IP addresses in IPv4, and we're running out at an alarming rate. So sooner or later, we may run out of IPv4 addresses altogether, probably before your lifetime. And if that happens, IPv4 becomes unusable when we completely run out of addresses. So one of the things that we want to do with IPv4, since we're using it, since it's the model that we've been using for so long, is we're going to keep using it, and we're going to try and conserve addresses whenever possible, and that's where subnetting comes in. All right, let's go ahead and take a look at the next slide. IPv4 address structure. This is going to give us the real, the nuts and bolts of IPv4. It is a 32-bit value. Those 32 bits are 4 bytes, and each byte is separated by a decimal point or a period, whatever you want to call it. And the numbers, as you post them in, will be single values of decimal representing that byte of information. We did some slides earlier where we did binary and hex and decimal conversions. Remember, in a byte of information, which is 8 binary digits of zeros and ones, which you're seeing kind of in that gray section down below, there is a corresponding for every single section there that you see. There's a corresponding decimal value that you can correlate with that. So 11 followed by 6 zeros equals 192 in decimal. As humans, we like decimal. The machines read it in binary, and they're actually reading in a pattern function. The other thing that they want you to be aware of is that an IPv4 address has 2 parts. It has a network portion, and it has a host portion. In most cases, in most systems that you're familiar with in the entire world, if you have 2 values that you need to keep track of, you make 2 different fields for them. You say, this is our network field, and this is our host field. In IPv4, we didn't do that. What they did is they said this. Let's take one value, and that one value can be used as both a network and the host value. What? And wait, it gets better. Depending on this other value that we use, the subnet mask, when applied, a single IP address could be in different networks based on the subnet mask, which is going to define how many of the bits, of the 32 bits, are going to be used for the network size. Obviously, the more bits that are used for network, the larger number of networks you could create. Also, that would leave, since it's 32 total bits, if we use more bits for network, that leaves fewer bits for hosts. Fewer bits for hosts means less combinations of binary digits for hosts, and therefore we would have smaller networks. So the more digits that we use for network, the less digits we use for host, the smaller the networks are going to be. So just keep that in mind. Let's move on to the next slide. Subnet mask, and we just spoke of the subnet mask and how it works. And really, the best way I can describe the subnet mask, and you're going to hear this in following videos too, is it's a series of consecutive ones until it turns to 0, and it's really, really simple. If we look at this subnet mask here, we're going to apply it bit by bit to this IPv4 address. So this bit right here, this very first high order bit, is corresponding with this high order bit right here, this bit right here. And this bit here is corresponding directly with this bit here, and everyone in between is directly corresponding with the one that's right below, above or below it. Okay? All the way through, and that is true all the way across through the entire IP address. So we have a 32-bit IP address, and we are going to apply a 32-bit subnet mask to that address. Okay, sounds good. Now here's the thing. The subnet mask is a series of consecutive ones, which basically says this. If the subnet mask value is a 1, the corresponding bit in the IP address is designated to the network portion of the address and not to the host portion. The host portion is designated by a 0 in the subnet mask value. In this particular case, this is a subnet mask that is called a /24, and we'll get to VLSM pretty soon. But it's called a /24 because there's 24 digits, 8 and 8 and 8, that are all set to 1. And if all 24 of those digits are set to 1, that makes it a /24. That leaves us 8 digits over here for host. If we have 8 digits for host, just very quickly, that's 2 different values for each. That's 2 to the 8th power, and that means there's 256 total addresses that we could create with 8 digits left. So 1 byte of information, as you know, can be a decimal value between 0 and 255. Each one of those represents a unique binary combinations of zeros and ones, and that's 256 total combinations, and that's what you get with a /24. All right. Let's move on to the next slide. Next slide just talks about the idea of prefix length, which is where we were just at. We were just right here on the subnet mask being a /24. /24 is great. It means that your network can have as many as 254 total addresses, but it'll have 256 total values that you can use. There's 2 addresses that you cannot use, and we'll get into those in just a minute. But of the 256 addresses that are total, only 254 would be available. You can't use the first, and you can't use the last for any given host. But the prefix of a /24 gives you an idea of what's left. And the reason for that is once again, there's 8 binary digits that will allow that to happen. Okay? If we moved up just one box here, and we start looking at this particular format, 255, 255.00, that means that only the first 2 numbers of an IP address would be designated to the network section. That means the last 2 numbers would be designated to the host section, and that means that with a prefix length or a subnet mask that is only 16 digits long, that would leave the network being 16 digits, and then the host portion being 16 digits, which would be 2 to the 16th power of digits, which is 65,536 total addresses, which if you multiply it out is 256 times 256, because there's 256 in each one of those octets of combinations, and you could uniquely change each one of those. So just keep that in mind. I don't know, like I said, we're going to dig into this deeper in future PowerPoint presentations and videos. But this is just giving you an idea. Right now they're just saying, look, we got this value, we got this number, it's an IP address. It's going to represent the network and the host. And the way we're going to tell if it's network or host is we're going to apply this other value called a subnet mask to it. And the subnet mask is going to define how much of the addressable space is used for the network, and then whatever's left after that is for a host. And a 1 defines network, and a 0 defines host. Easy enough. All right, moving on. Let's go ahead to the next slide. Whoops, that's not the next slide. That's the next slide. So this talks about the concept of ANDing, and I'm not going to teach you this at all. You can take a look at it, and it's okay, but I'm not a huge fan of Boolean ANDing. What I want you to identify is this, is that there's a pattern that's attested to this. But this will work. And, the ANDing just basically says this. Well, what you can get is a network address out of ANDing an IPv4 address and a subnet mask. And it will give you the IPv4 network address, the first address in the range, if you AND them out. Okay. Just be aware of that. I haven't even told you what the network address is yet. So let's just hold off on that. Because on this slide, we talk about what a network address actually is. I probably should have reversed those slides and not just left it to Cisco, but this is how they put them in order. So there are some special addresses that go along with every given network. So this slide does a really nice job of breaking those out for you. And it says each network has three different types of addresses. There is a network address, there is a host address, and there are broadcasts. There's a broadcast address. Now, here's the deal. In any given range of addresses, like a /24, as we said before, in a /24, that leaves the fourth number being set for host. In that particular case, that means that the first address in that range, like if we look at what we have in this diagram here, that network is 192.168.10. dot something, right? Some of the there's a .1, there's a .10, there's a .101, there's a .12, and so on and so forth. And each one of those hosts has got an address that's somewhere in this space. Now, here's the thing. The network address, sometimes also called network ID, is going to be the first available address in that space. And the first available address in that space is going to have a binary readout of all, in this case, all 8 zeros in a row. So 8 zeros in a row, 1, 2, 3, 4, 5, 6, 7. 8 zeros in a row, that's going to be a binary equivalent to the value, or decimal equivalent to the value of 0. That's the first address in the range. Now, the broadcast address is, I'm just going to write bcast right here. The broadcast address is going to be the last possible address in the range. And once again, with this /24, it makes it really, really easy because it would be 192.168.10.255. 255 would identify the host portion of the address. And if we looked at the binary equivalent of 255, that would be 1, 8 ones in a row. And every number in between, like 1 and 10 and 101 and whatever else you want to throw in there. For hosts, these hosts here, and for that interface, these are all going to be just regular old host addresses that are going to be between 1 and 254 in that fourth octet. And the first address, the network address, will be the first one, which will be 0, and the broadcast address will be the last one, which will be 255. In any address, no matter, in any subnet, no matter how big or small, 65,000 addresses, 1 million addresses, 4 addresses, 2 of the addresses are always used for overhead. The first address is always a network ID, and the last address is always a broadcast ID. Always, always. There's no changing that, and you cannot use those as hosts. So network address can't be a host. Broadcast address can't be a host, but a host address can be a host, and it can't be a network or a broadcast. First is network, last is broadcast. Everything in between, no matter how big, is a host address.